We'll solve a basic question to understand and elucidate the concepts that we have developed in the previous two videos. So what the situation we have over here is we have an inclined plane which is at an angle theta, and there's gravity force acting vertically downwards, and we have a block of mass m which is resting on this inclined plane. Now if this inclined plane did not have any friction, this block would simply slide down. And the question is that we do have friction and the coefficient of friction is 0.5. The question is at what angle theta will the block slide down? Because as we start increasing this angle theta, what we can intuitively see is at some point the block should slide down. So let us solve this problem. As usual, we'll make an isolation volume around the block of interest. So we cut this over here and we make this block. Now, as in the previous lecture, we had said first we make an FBD. So we've made the FBD. Then we add all the forces. So the first force that we add is weight, which is mg. The next force is the normal reaction, which is in this direction, N. And as we can see that these two forces by themselves cannot balance this out, so we add a friction force in the direction that we feel it has to be applied in order to oppose sliding. So in this case the block will try to move downwards, so we have a friction force which acts upwards. Now all we need to do is we need to balance the horizontal and vertical components of the forces to get N and F. So we will change the x direction is this, and this is the y direction, and using this we take the components of weight. So along this direction the value of our weight is mg cos theta. You can confirm this for yourself. And along this direction the value of weight is mg sin theta. Now balancing forces along the y direction, that is in this direction, we get that N is equal to mg cos theta. And we can confirm this, we can make sure that we're not making a mistake by setting theta to 0. So when theta is 0, this plane is horizontal, and in that case we know that the normal reaction is equal to mg, since cos 0 is equal to 1. So this we can confirm is not a mistake, 1. And balancing forces in the x direction, we can say that F is equal to mg sin theta. Now what we want to know is at what angle theta will the block slide down. So in order for the block to be in static equilibrium, F has to be less than equal to F critical. This is what we had seen in the previous video. And as soon as F is equal to F critical, it is in critical equilibrium, that is just a bit more than that, and it will start sliding. So we know that F is equal to mg sin theta. This is equation number 2. And we also know that F critical is equal to mu s into n. And from the first equation, we can say that this is equal to mu s into mg into cos theta. So converting this inequality and taking its boundary case and setting it to be an equality, we can say that the body will begin to slide at an angle at which F is equal to F critical, and this will be when mg sin theta is equal to mu s mg cos theta. You can just divide both sides by mg and get that tan theta is equal to mu s, hence theta is equal to tan inverse mu s. So as soon as we cross an angle theta whose value is equal to tan inverse mu s, this block will start sliding. Now let's see intuitively if this is true. Now what we have seen is that for rough surfaces or surfaces with more grip, the value of μs is more. And we know that through the tan inverse function that whenever the value of μs is more, the value of theta is more. And we can intuitively see that if the two surfaces have a better grip, then we can increase the theta more before m starts to fall. Hence, if μs is more, then this value of theta is also more, which is something that we can intuitively confirm. Before attempting this question, keep in mind that friction always opposes the direction of motion. That is, change the direction of friction between the two cases that have been mentioned here.